Okay, let's begin our discussion about section 6.5, lines with initial condition. So far we have discussed the behaviors of signals on the transmission line, and up to now we all assume that there are no signals on the line, which means the transmission line is not charged, contains no energy. However, the analysis can be started with the so-called arbitrary initial condition. Now, you don't have to begin your analysis at t equal to 0. You can start anytime, which means there may be currents and voltage signals already on the line. As long as you know the so-called initial condition, you know the current and voltage distribution on the transmission line, and then you can find out what's going on or what the signals will become in follow-up analysis. So let's begin with an example problem as shown here. And in this figure, we have a piece of transmission line which is open-ended on both ends. So what does that mean? Well, just piece of wire, piece of transmission line, and the both ends are terminated with open circuit. Not that open circuit do not consume energy, either, and so does the short circuit. Both open circuit, short circuit, and actually reactive loads. I mean inductors and capacitors. They do not, short and open circuit do not absorb energy, they just reflected the energy. Inductor and capacitors may store some energy. However, they do not dissipate energy, do not consume energy. So only resistive load resistors will consume energy. So so to the left is the configuration of the transmission line. You see the characteristic impedance is 50 ohm. The line length is equal to a propagation delay of 1 microsecond, which can be interpreted as 300 meter long if this is a air transmission line. Okay. And to the right are the voltage and current distribution on the line. And be careful about it because the plots only shows the so-called total voltage and total current. For transmission lines, the voltage and current signal will not stay. They will travel, they will propagate on the line. So what is the implication of the total voltage and the total current? They can be divided as positive going and negative going signals. For the total voltage, it should be decomposed into V plus and V minus, which the V plus signal goes to the right and the V minus signal goes to the left. And so does for the current distribution. It also contains I plus and the I minus signal. So how do we know the exact distribution of the V plus signal and V minus signal, I plus and I minus signal? Well, they are not that difficult to find because we can write down relationship like this. So equation 6.60 A and B describes the relationship between total voltage and total current, which are simply the sum of V plus and V minus, I plus and I minus signal. And because we know that both the positive going and negative going signal shall abide the rule of characteristic impedance. In other words, the voltage will be Z sub 0 times the current. Okay, so you have this relationship I plus equals to V plus divided by Z sub 0, and I minus equals to minus of V minus over Z sub 0. The minus sign simply is the result for having the signal going from right to left. Okay, so which means equation 6.60b can be replaced with unknowns as V plus and V minus. So we substitute I plus and I minus into equation 6.60b, and we end up with this equation: B plus minus me minus V minus equals to Z sub 0 times total current I. So we have two unknowns, V plus and V minus, and the rest are given by the initial condition and the characteristic impedance of the transmission line. So we can find out the percentage of how much. We can figure out what V plus is and what V minus is, as long as you can provide me the total voltage and the total currents on the line, right? And look at the distribution of the total voltage and total currents. Note that they appears in the form of the so-called piecewise continuous. 是什么意思啊？折线啊，折线连续啦，所以，图画成这样子也是故意的啦，方便你算，不然你要画成曲线的话，你每一个点都要去解二元联立方程式，那题目这边画成是 piecewise continuous， 所以然后你会看到它就左边一个点，右边一个点，还有中间一个点嘛，所以每个点你要去解一个二元联立方程式，你的未知数是 V plus V minus 已知嘞 total V、total I 还有 Z 0嘛，所以根据图片给定，你去写出左边那个点的二元联立方程式，右边那个点的二元联立方程式，以及中间那个点的二元联立方程式，那你就可以解出左中右的 V plus 是多少 ，V minus 是多少，那 I plus I minus 多少，就用前面讲过的那个 I current 跟 voltage 的那个 Z 0倍的那个关系去找就有了，所以这个题目其实只是考你的小学6年级的算术吧，只是考你把二元联立方程式解出来而已，Okay, so we know that the plots are shown as piecewise continuous graphs, so you can find out the V plus and V minus signal at a specific point, according to the voltage and currents on that point. So as you can see here, I mark the V plus and the I plus with 3 circles, which are located in the middle, on the left, and on the right, which are so you need to solve equations at these 3 positions so that you can have the variation of V plus and V minus signal. So here's one example. To the left is one example. So suppose we try to solve the V plus and V minus signal at where? On the left. So as you can use this relationship, that will be half of the total voltage, which is 50 in this place, and plus Z sub 0 times I. So Z sub 0 is 50 ohm, and the current is 0 amp. Is 0 amp. So the V plus at Z equal to 0 is 25 volts. And if you do the same for the V minus signal, which turns out to be the total voltage minus Z sub 0 times the total current I, it appears as 25. Okay? So on the left hand side, V plus signal is 25, V minus signal is 25 as well. And if you solve, so here is our result. Okay, according to the initial total voltage and initial total current, use this two relationship, we find out the total voltage here is 25. I'm sorry. V plus voltage here is 25, V minus voltage here is 25 as well. V plus voltage in the middle is 50. V minus voltage in the middle is 0. And the V plus voltage here is 0. As you can see here, the total voltage and total currents are both zeros. So it's kind of trivial solution that the V plus and V minus are both 0. Okay, so use this relationship, you can find out the distribution of V plus signal and V minus signal. Okay, so on that plot, you notice that I marked the red arrow. What is the significance of those two red arrows? They shows up which direction is the signal going, which direction. The V plus signal is going to the right. The V minus signal is going to the left. So right now we have these are the voltage distribution at the time instant of t equals to 0. What happens at t equal to 0 plus? So what happens if the time progresses a little bit? Well, the V plus signal over here will shift to the right. Everything will shift to the right. However, the very tip at a position Z equal to L, that is marked with A, has no place to go. Because the transmission line, the length of the transmission line is L. So what happens with A? Well, it gets reflected because it's an open circuit. So what is the reflected circuit becomes for position A? Well, the reflection coefficient is 1. So it gets reflected, it becomes part of the V minus signal. And its magnitude is the same, and its polarity, 它的那个正负号 polarity, its polarity is the same as well. Okay, so A, the very tip of the forward going signal, will appear on the right hand side of the reverse going signal. And you can imagine for signal C over here, it will move forward to the right, and the left end of the CD signal will also get reflected from the left hand side, and because it's open-ended as well, the reflection coefficient is 1, 2. So this part will follow up the forward-going signal and proceed to the right. Okay, so it's kind of a circulating signal. Now, moving on the transmission line, because why? Because the transmission line is lossless, and the termination, the open circuit termination, do not consume energy as well. So if this kind of transmission line, I mean lossless transmission line, is obtainable, then our society can obtain the so-called nirvana. Nirvana 是什么？极乐世界啊 ，OK。这个东西要是真的有的话，我们就已登极乐了啊。为什么？ 没有能源问题啦。哦，现在能源问题在哪里？储存嘛。啊，所有的储存装置都牵涉到能量的转换。哦，那所以今年年底有一部重要的电影叫做什么？忘记那叫什么？潘朵拉不是潘朵拉，那叫什么？阿凡达2 OK， 小时候有没有看过？你确定你还记得？你只看到那个蓝色大精灵，对不对？哦，我不晓得，应该小时候不知道几岁的时候看的哈。OK， 好啦，阿凡达那个故事，它是在建立在一个前提假设上，就是某一个星球上，那个潘朵拉星球上有一种元素叫做 unobtainium， 它的名字告诉你就是黑西伯扣林的代际哈，你是无法得到的哈。但那个东西哈，它有一个重要的特性叫什么？常温超导体常温超导体。那常温超导，常温是什么？起码要是零下个40-50度以内的吧，像那个高温超导体好像是100度 K 叫高温超导体那离常温超导体还很远。没有，有人声称他们做出常温超导体了，然后也用实验证明了，可惜那个结果基本上还是没啥效果用了，不好意思录进去了 ，OK 为什么？因为他们虽然可以在常温，也就大概300度 K 的时候弄到观察到超导效能，但是他们需要把那个材料用大概100万个大气压力把它压住，所以要做到100万个大气压力的那个压力那么大，把它挤住那个所需要的能源大概又远高过它的那个实现超导的耗损所以还有长长的一条路要走了假如说人类能够弄出常温超导体的话，好了，那潘朵拉星球的话，它是建立在常温超导的那个前提之下那假如有的话，那真的是有的话就别对吧？OK 好，但所以实际上你不可能看到这种现象，这种现象就是告诉给你一段传输线，然后我灌了一些电压电流讯号进去，然后它这个里头一直绕，不会耗损，不会耗损。那这样的话，那个我们就可以拿着这样的电池，然后跑到什么戈壁沙漠，然后拿太阳能板晒太阳，然后晒，然后充好多电，然后回来你家20年的电都用不完了这样子。但事实上没有办法嘛Okay, but anyway, let's go back to the problem. So providing that you don't have loss on the transmission line, and because the termination are lossless as well, the signal will remain on the transmission line and cycling in the transmission line for a very long period of time. But the truth is, because of the loss on the transmission line, well, the signal for a realistic transmission line, the signal shall bouncing back and forth between the two open ends for several times, but it will die out eventually, okay, due to the loss on the line. And another thing that you need to be careful is the boundary condition. You see, the current distribution are 0 on both ends. This is the result of the boundary condition, which are open terminations. Because at the open termination, the current must be 0. For short termination, what is the boundary condition? The voltage must be zeros on short termination, and the current must be 0 at open terminations. Okay, so here we see because they are open terminated, so the voltage on the ends can be either 0 or 50 or any other values, but the currents must be the total current must be 0 at the termination. All right, so let's move on to discuss the next matter. Suppose that we wish to find the voltage and current distribution at some time later, say 0.5 microsecond. What can we do to find out the voltage on the line, a voltage and current distribution on the line? Well, to do this, we can proceed as with our previous result. In the previous slides, we separate or we decompose the total voltage and total currents into V plus and V minus signal. And I already explained that the V plus and V minus signal, the forward going and reverse going signal will travel in the transmission line as the time progresses. So according to the prescribed time delay, that is 0.5 microsecond in this case, what happens? Now let's see. Okay, what happens? The first half of the V plus signal will reach the right end and get reflected. So this part, this is the distribution at t equals 0 microsecond, correct? Then the first half will get reflected back into as the V minus signal. And as you can see, the magnitude do not change. The magnitude and polarity do not change because the reflection coefficient here is 1. And the second half of the V plus signal shall shift it to the right of the V plus signal. So you see, this is AB. It appears at the end of the V minus signal. And signal BC will continues move forward and become the right half of the V plus signal. And the last thing, the CD signal, which appears on the left half of the V minus signal, will get reflected from the left open end and becomes the second half of the V plus signal. So it appears here as CD. Okay? So step 1 is decompose the V plus, total V and total I currents at t equal to 0 into V plus and V minus. The second step is move the V plus signal and V minus signal according to the boundary and according to the prescribed time. And then the third step is what? Is adding up the V plus and V minus signal so that we can have the total voltage. So you add up the two, it becomes this. That's the total voltage signal. And here is you can do the same for the current signal, okay? So you need to divide the V plus signal by 50 to get the I plus signal. And you need to divide the V minus signal by 50 and times a minus sign, so you get the I minus signal. And you add up the two. You add up the two, and it appears as this. That would be your total current at t equal to 0.5 microsecond. Okay? So you need to practice this kind of problem in your homework and possibly in the sample exam problems, because I'm not guaranteed that they shall appear in your midterm problems, but well, the probability is about 50%. Okay? 很有可能啦，很有可能。 像 bouncing diagram 是100%啦，哦，这个大概 50% 哦，所以还是要这个也不难嘛，对不对？哦 ，Alright, and so let's move on to our next topic. So still talking about initial I'm trying to summarize our previous of this problem. Okay, so suppose that we connect a resistor of value z sub 0 at the end, z equal to L at the t equal to 0. The reflection. So what happens? Originally, we have a open circuit transmission line. So the signal is bouncing back and forth between the two ends because the line itself is lossless. The open-ending termination are lossless as well. But for this case, at a t equal to 0, we connect a resistor, say, which is, what is the value? Oh, z sub 0. Which is the same as the characteristic impedance of the transmission line. So that at t equal to 0, we connect a resistor of z sub 0 on the right-hand side. So what happens? All the V plus signal that reaches the resistor will be absorbed because this is a so-called matching load. Matching load 注意啊，跟传输线特性阻抗相同的负载，我们叫它 matching load matching load 匹配的匹配的负载。那因为是匹配，所以反射系数等于多少？等于0。那意思就本来在传输线下面的能量就被这一个 matching load 给吃掉了。那原本我们看到的那个讯号分布长什么样子？讯号分布长这样吗？这 V plus 还是 V minus？ 所以你可以告诉我，需要多久的时间，我们可以把所有的能量吃光光？这个 resistor。1.5个 microsecond 嘛？为什么？因为整条线长是1个 microsecond， 线长是1个 microsecond， 而讯号看起来是一条总长为 1.5个 microsecond 的火车，从 A、B、C 到 D 这样算起来的话，我们刚刚的那个图你还记得的话，它是 1.5个 microsecond 长，那你只要在 t 等于0的时候，从右侧接上 matching load 的话，那往右走的讯号就被吃掉，所以完整的讯号会在 1.5个 microsecond 的时间内被这一个 resistor 完全吃掉。Okay, so let's go back to the slide. And because the reflection coefficient at the right end is 0 after connecting it with a 15 ohm resistor, the forward going wave, the positive going wave, as it impinges on the resistor, get absorbed in it instead of producing the reflected wave. So there will be no reflected wave. And the line therefore completely discharged into the resistor by the time t equals to 1.5 microsecond with the resulting time variation of voltage across RL as shown in the next figure. Okay, so this is the time domain plots of the loading resistors, which equals to 50 ohm in this case. So at t equal to 0, it sees the front of the signal, which is marked as A, and it says B, C, D. And at the time t equals to 1.5 microsecond, the transmission line, the energy on the transmission line is totally discharged by RL, by this resistive loading. Okay. And now let's move on to another problem, another example. So this is the second example we will examine today. This is a transmission line loaded with uniform initial voltage and current distribution. The analysis can be performed in the same manner for as the arbitrary initial condition for voltage and current. So let's take a look at the problem. So here we have a transmission line. So prior to the switch is closed on, which is take place at t equal to 0, you have a transmission line with both ends open terminated, and the transmission line is charged with a voltage, a uniform voltage of 100 volt. Okay? And the total current on the line is 0. So you have total voltage 100 volt, you have a total current 0 on the line. So what is the V plus component and the V minus component? That would be 50-50 again. Well, or you can say there's no moving charge, okay, in this case. Or you can think of it as 50 volts of V plus and 50 volts of V minus with 0 I plus and 0 I minus. Yeah. 好了，那因为它是均匀分布的嘛，所以它没有电流流动，所以 I total 等于0嘛，所以 I plus I minus 都等于0，那你的 V plus 跟 V minus 只好变成正50-50嘛，但这个不重要了，也不是说不重要，这个就一开始的 initial condition 就是均匀分布的电压电流。均匀分布的电压，然后电流为0，所以事实上讯号没有在动，所以你可以把它看作是什么？它是一个充饱电的电容。为什么讲充饱电的电容？我不讲充饱电的电感，为什么？因为在传输线，对，你可以讲说因为在传输线中，电压是类比于电场那电流是类比于磁场。那在这个讯号里头，我们只有电压讯号，所以表示能量都是以电场的形式储存。所以当然一个比较合适的讲法就是说，它是以电容的形式在储存能量所以这是一个偏向一个电容的结构。那当然事情在开关关上之后就不一样了。事情在开关关上之后就不一样。我们先不要去管那个 V plus V minus I plus I plus 这些细节。开关关上之后会发生什么事？电容放电放到哪里去？放到 RL 去嘛。然后 RL 因为本身是电阻，所以 eventually 所有的能量原本灌在那一条传输线上面，能量会被 RL 吃掉。所以好了，你至少知道事情的结局了我们先剧透完了嘛，对不对那个能量最后会死光光OK 所以场上的每个人都要死这样子，就是你去看那个恐怖片的时候都这样OK but anyway we need to provide some calculation so we need to do the so-called transient analysis. So we need to know what happened. Okay, so you are more interested in how the characters are killed in the horror movie, huh? Not the result, huh? Okay, you know, for horror movie usually everybody get killed. Right? Wow, that sucks. All right, so in this case, the resistor, the loading resistor is 150 ohm, which makes the problem a little bit more interesting, right? Otherwise, if it connect with a 50 ohm load, then well, just signal will be dumped into energy will be dumped into the matching node, and nothing interesting happen on the line. However, in this case, the termination is 150 ohm, which is not matched with the characteristic impedance of the transmission line, and we can calculate the reflection coefficient here is what? What is the reflection coefficient? Well, if you cannot calculate it in 5 seconds now, you are supposed to do that 2 weeks later. Okay, try to calculate the reflection coefficient in 3 seconds. So for this case, that will be minus 100 over 200. That will be minus 0.5. Minus 0.5. The reflection coefficient here is minus 0.5. And what is the reflection coefficient here? 1. Plus 1. So what we know is once the switch is closed on, the sum of the energy will be dumped into the loading resistor. And the effect of this connection will propagate to the right. The effect will propagate to the right. So we suppose there is a positive going signal referred as V plus and I plus appear at t equal to 0. Appear with the switch closed on. So we can write a few equations to find out the amount and polarity of V plus and I plus signal. So according to the voltage division law over here, the boundary condition is total voltage, that is V sub 0, the original, the initial voltage on the line, plus V plus, the newly generated V plus signal, the total voltage divided by the current, which is I plus for this case, should be equal to RL. Note the equation is written as V sub 0 plus V plus equals to minus. Why? Because I plus signal is defined as it's going to the right. But you know, to build up a voltage like this, the current should go this way. So which happens to be the opposite direction of the boundary condition. So we put a minus sign in the equations to stand for this scenario. Okay, so the total voltage V sub 0 plus V plus equals to the minus of I plus times RL. All right? And what do we know about this? Oh, IL equals to 150. We also know that I plus equals to V plus divided by 50. So by replacing I plus with V plus, we can solve for V plus and I plus as well. So V plus can be found using the relationship. It's equals to minus 25 volt. And I plus equals to minus 0.5 amp. What is the significance? What is the implication of I plus current as a negative current, which means we define it goes to the right, but it actually goes to the left. But anyway, the effect of the appearance of I plus currents will propagate to the right. Even though the actual charge are moving to the left, the actual currents are moving to the right, but the consequence will propagate to the right. And the right hand side of the transmission line will eventually notice, oh, something happens at the other end. The charge on the transmission line will flows again and discharge into the RL loading resistors. All right, and we know that the V plus I plus signal start at t equal to 0 will propagate to the right and get reflected, because on the right hand side we have reflection coefficient of 1, so you will have V minus and I minus signal. And the V minus I minus signal that arrives to the left hand will get reflected again, because the reflection coefficient here is what? Is 1 over 2.哎，我算错了，要死，不是负1/2，是1/2。真糟糕，翻车了。150减50啊，除上200will get reflected. Okay, so the bouncing back and forth, the phenomenon of bouncing back and forth currents and voltage signals will continue on the line for a certain amount of time. But eventually, as we know, all the energy will go to the resistor. Okay, so to characterize what happens on this transmission line, we can draw the bouncing diagram. Okay, so the first thing, draw a horizontal line marked with the reflection coefficient on the left and the right hand side. Originally you have a 100 volt voltage signal on your voltage bouncing diagram. The initial V plus signal is -25, so you will observe the signals, and the -25 signal will get reflected as another -25 signal, but it propagates to the reverse direction. So the total voltage on the right hand side will be 100 volt from t equal to 0 and 1 microsecond, and will becomes what? 50 between 1 and 3 microsecond. And to the left, the voltage, total voltage will be 75, which is 100 minus 25. But starting at t equal to 2 microsecond, it will appear as 37.5 due to the presence of V minus signals and V minus plus signal. So you should complete this bouncing diagram and find out the time variation on the transmission line. Okay, so if we keep track of the time variation, voltage or current time variation at a specific point, we can draw a plot like this. This is drawn at which place? Z equal to 0. Okay, that's the left hand side. So at t equal to 0, before t equal to 0, it's actually 100. 所以其实应该再画一条100啊。好了，然后到 t 等于0的时候，它就掉下来哈，因为 v 正等于-25。好 ，so at t starting at t equal to 0, you have 75 ohm, and then at t equal to 2 microseconds, it's 37.5, and then it becomes 18.75. Well, you see they get halved every 2 microseconds. So it will eventually vanishes in terms of from the perspective, from the engineering perspective, okay? But from the pure mathematical perspective, it will last forever. But well, that's not the case for engineering. All right. All right. So what we observe on the transmission line is the voltage decreases as the time progresses, and eventually they are consumed by the loading resistor, which is 150 ohm on the left hand. So what happens? What happens? In terms of physics, the energy is delivered to the resistor as the time progresses. The energy density on the transmission line can be interpreted as per unit length capacitance and per unit length inductance. In reality, they are, in transmission line theory, they are stored in stored in inductors and capacitor. But in reality, the energy stored on the transmission line are stored in terms of electrical field and the magnetic field. Okay. So what can we do is find out the total voltage, the energy stored on the transmission line. So equation 6.66, A and B represents the energy stored in terms of electrical field, energy stored in terms of electrical field, and energy stored in terms of magnetic field. For electrical field, the energy stored can be represented as 0.5 times C times V to the square times the length of the transmission line, okay? And because the C stands for per unit length capacitance, so it will becomes the real capacitance by times it with the length L, okay? And L, the length, can be replaced with propagation velocity V sub p and the propagation time required, which is marked as capital T. And V sub p, the velocity of propagation, can be replaced with 1 over square root of L times C. So you times, if you combine them together, it appears at Z sub 0. Z sub 0, the characteristic impedance is what? It's the square root of L over C. So the energy stored in terms of electrical field can be represented as half times V to the square over Z sub 0 times T, the propagation delay required. And for the energy stored in terms of magnetic field, it can be shown that it equals to half times I to the square times Z sub 0 and T. So for the example under consideration, V is 100 ohm, total current is 0 everywhere, and so Wm equals to 0, and We, the electrical field, the energy stored in terms of electrical field can be calculated as 10 to the minus 4 Joule. 10的负4方焦耳，就用 6.66A 算出来了嘛，100平方除以2除以50乘上10的负6，等于10的负4焦耳。And this is the initial current, initial energy stored on the transmission line. And we can also calculate the power dissipated in the resistor. Because we observe this result, this is the voltage across the resistor, starting from t equal to 0 microsecond. So in the first 2 microseconds, the total energy consumed by the resistor can be integrated here. And you can do the same thing for 2 to 4 microseconds, 4 to 6 microseconds, so on and so forth. It forms an infinite series. And you can find out that the summation of this infinite series is 10 to the minus 4 joule as well. So you can satisfy the balanced energy conservation principle. Okay, so the stored energy on the transmission line is completely dissipated by the resistor. So by comparing the energy calculated with this two relationship, with these two equations. Okay.